Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Larissa Luciano Amorim with us today. Hi, Larissa.
Hi everybody.
Let's see. And Larissa, where are you located at?
Right now I'm in Brazil at Rio Grande do Sul, the most south part of Brazil.
Very cool. Very cool. So we're going Southern Hemisphere today. So we're halfway around the world in the other direction. So very cool. Let's see, it's Southern Hemisphere. So is winter coming up in Brazil?
Yeah, actually last week was very cold, but this week is hot again. It's becoming unpredictable weather. It's fall, so it can have hot days, cold days.
Very cool.
Swing back and forth.
Very cool. And what is
we have yellow leaves on the trees.
Okay, so you know it's coming.
Yes.
Does it snow there? Do you get ice?
Not really. Just up in the mountains. We have some mountains here on the state, and up there it can snow, but usually it doesn't.
Okay. Okay. Curious. And what is your position there in Brazil?
Right now I'm in the second year of my PhD.
Very good.
And I'm working with Kepler and magnetic white dwarfs.
Very nice. Well, I look forward to calling you Dr. Larissa here in a little bit. So that'll be very cool. Very nice. And Larissa, what do you like to do for research?
So I'm very interested in stars in general since I was in high school, and I always knew I wanted to work with stars. But when I was graduating, I fell in love with magnetic fields. So to work with magnetic fields in stars is perfect for me.
Awesome.
In undergrads, I studied subgiant stars and their magnetic field, and then I changed to white dwarf stars and their magnetic fields in my master's.
Very nice.
Which is also what I'm working on with my PhD.
Very good. All right. I'm definitely looking forward to Dr. Larissa. And that is going to bring us to this very awesome APJ article. It's the open access era, people. You can go get a copy for free. Go grab one. Catalog of magnetic white dwarfs with hydrogen-dominated atmospheres. And Larissa, take us away.
So this article was the result of my work doing my master's with my advisor, which is Kepler. And we have some collaborators that collab who helped writing the code that we used. And Jordan who wrote some models for the code. And Alejandra who helped with the more evolution part. She is also a professor here in the group research, in the research group.
Very nice. Good shout out.
So this article is basically this compilation of more than 800 white dwarf stars with hydrogen-dominated atmospheres. And we computed the magnetic field for them. Previously in the literature, there has been already some smaller catalogs. There is a catalog of about 400 stars, but it's not with detailed determined magnetic fields. It's more only a visual inspection. So this deep characterization was done only for less than 200 stars. So this is the big point of this article.
Yeah, this is a significant expansion of the number of deeply interrogated magnetic white dwarfs.
Yeah.
Very cool.
So the basic thing is we have detected magnetic fields in stars, especially in white dwarfs, for a long time now, but we still don't know exactly what their origin is. Some stars, especially in magnetic white dwarfs, some may already have a magnetic field in a previous stage of the evolution. We measure magnetic fields in main sequence stars, for example, that can lead to a magnetic white dwarf. It's an option. We call that fossil fields. It's known that some white dwarfs that exist today in single white dwarfs are actually the result of mergers. So a binary product. So in the merger, during the merger, It can arrive dynamos that can generate magnetic fields. So that would be another option for the surging of magnetic fields.
Right.
And actually, while the white dwarf is evolving, after the white dwarf is formed and is cooling,
Yes.
it can some mechanism can also appear that generates magnetic fields.
Okay.
So it's basically 3 moments of the white dwarf, like before it's born, while it's burning, and after when
There you
it's
go.
cooling.
Very cool. Good.
The thing is, we want more information possible to help to solve this question, and this catalog helps with that because it's a bigger sample, and with bigger samples we expect to develop better statistics, because if you have a smaller sample you may have some specific cases and think that that's a general behavior, but that's not true. So the bigger the sample, the better.
Absolutely. Very good.
Our sample is composed with slow and digital sky survey data from the data release 16. The previous catalog that I mentioned that have about 400 stars is from DR data release 7.
Okay.
So it's not in terms of new magnetic fields, new magnetic white dwarfs, is not a bunch of new detections, because the slow and digital sky survey changed how it chooses its target. So we don't have a lot of new, even though we have much more new observations, they are not focused on white dwarfs, so we don't have a lot of new detections of magnetic white dwarfs.
Okay.
The way this article goes is, as the previous surveys, we first look at the spectra visually. So there was a very hard work that my advisor started, which is looking at each spectra and identifying if the absorption lines of the hydrogen have a split on them, because if there is a magnetic field, this line is going to split into components because of the break of the degeneracy. After we identify that they are white dwarfs with splits in the absorption lines, then we put them through the code that examines in more detail the magnitude of the magnetic field, because with our eyes we can only say there is a magnetic field there, but the code, it analyzes how the magnetic field is distributed on the stellar disk that we are observing. So we only used off-centered dipoles inclined in relation to the line of sight. But this code can also use quadrupoles and bigger orders. But if you use an off-center and if you use an inclination, the results are very pretty accurate, actually, in the models when you compare to the observations, and it doesn't make the computational so heavy, because if you make an octupole, it's very heavy computationally. So it's an easy mathematical way to get an expansion, because if you expand in series, deep dipole that is off-centered, you can have a component that is a centered dipole and a centered quadrupole and octupole, and it's equivalent to summing a lot of orders of the magnetic component.
I'm with you. Good.
So yeah, we use the off-center dipole, and the code, it computes how an off-center dipole we have, what is the magnitude of the field in each little region of the star, the stellar disk, and then it sums up all the effects, making spectra that we can compare with the observed spectra.
Cool. Very cool.
So the models that we have, they range between 8,000 Kelvin and 50,000 Kelvin, but we didn't have any models converging at 50,000 Kelvin, so we limited to 40,000 Kelvin.
Okay.
This is, with our sample from SDSS, this is pretty good, actually, this range. There were some stars that were cooler than this, like below 8,000 Kelvin, and that shows in the depth of the line mainly, but it doesn't affect the detection of the magnetic field itself, because the dispersion of the line, it depends only on the magnetic field and not on the temperature.
Good.
So we can measure the magnetic field either way, even though the depth of the model is not gonna match the depth of the observations.
Yes. Okay, I'm with you.
So I think we can walk through a little bit more on the article.
So it is a catalog. So here's part of the table. It is a machine readable table. So if you want to get the whole thing, go ahead and grab it. But these are some of the fields here.
So
where did the masses come from?
The masses and the temperature come from a table from the literature.
Okay.
So Gentili Fusilo already determined the mass and temperature for most of the stars.
Okay.
Some stars, they don't. These are determinations based on Gaia data.
Okay. Okay. Good. I'm with you.
So we didn't do the temperature and the mass, but there you can see a column that's called temperature from SDSS.
Yes.
That is from the photometry of SDSS.
Okay.
That we use because since some stars didn't have a temperature from Gaia, we needed to get it from somewhere. So we did it with non-magnetic models. So this temperature is based on non-magnetic models. So it's not that accurate.
Yeah.
But since the temperature is not gonna affect that much the magnetic field, the measurement of the intensity of the magnetic field, it's not a problem.
Okay, that's good. That's a model.
There you have the magnetic field intensity, the error bar, and the offset
of the dipole,
and the inclination of the dipole.
Right. Yep. Okay. Cool. Very good. Go get the whole table, people. And we want to do figure one?
Yes.
Sure, let's do figure one. Let's take a look. Here's a spectrum.
So here's an example. The magnetic fields we can measure with this technique, they range from 1 megagauss to 1,000 megagauss. Okay. So it's a pretty big interval range, yes. So the lower magnetic fields in this range, around 3 megagauss, is the first spectra, is an example of one. And it's already one example of a temperature that is below 8,000 Kelvin. So I put this spectra specifically to show how the lower temperature can affect the model and how the model is going to be different than the observed. You can see that, especially in H beta and the higher absorption lines, the depth of the line is not well modeled, but it's because of the temperature.
Right. Right.
They seem deeper.
Yes.
So the second spectrum, explaining, the black lines are the observed data and the red lines are the models. And the gray lines in the vertical line is where the lines should be if there were no magnetic field.
Oh, okay.
So they are the rest lines.
Okay.
It's just for you to have a sense of direction. And especially in the very higher fields, in the third spectrum, the last one on the bottom, it's a very high magnetic field, and you can see that where there's supposed to be H alpha and H beta, there's nothing.
Yeah.
And you can be confused like this is not hydrogen, but it is. It's just because the magnetic fields made the line go anywhere else.
Right. Moves
So
it.
just
Cool.
going back in order, the second one is a field of about 20 megagauss, if I'm not mistaken, and the third one 200 megagauss. So it's like each order of magnitude, 220, 200. And you can see how the spectra is affected.
And what is the signal noise on these spectra when you're taking them? What is the signal noise ratio on these spectra?
Unfortunately, our sample is very, very it has various signal to noises level depending on the spectra. So we have very good spectra with like 40 signal to noise, but we have others that are like 5.
Okay.
So it's not actually consistent through the sample.
That's fine.
Unfortunately.
That's fine.
But that's what we have.
I just wanted to make sure, right, signal noise wasn't like 10,000 or something like that. So it's a low res. It's all good.
No, yeah, it's low resolution.
All good.
Yep. The lower magnetic field around 3 megagauss, you only see the bottom of the line splitting. So you can sometimes, especially in H beta, you can see the shape of the shape of the line. You can see only the bottom that is splitted. But when you go to higher fields like 20 megagauss, like the second spectra, you can see that the line has actually, the whole line has splitted into 3 lines. Yes. It's not only the bottom of the line. You can see the 3 lines.
Right. Very cool.
And when you go to even higher magnetic fields, the lines actually go everywhere. And you can see that it's no longer recognizable the hydrogen spectra. Right.
Not something you would immediately pick up. Very cool.
Yeah.
Very good. Cool.
So we can go to the next figure.
Figure 2, what do we got here? Field strengths. Okay.
One thing interesting to look at is that, as I mentioned, there are already other catalogs that exist. The main ones are the Colab catalog, which also use the method that we are using, this code. So it investigates deeply the magnetic field, but it's not that big a sample. It's less than 200 stars.
Okay.
So you can see here that it's pretty good. There are some points that are really off. Especially you can see the bars. The bars get so distorted because the axis is in log scale. So
yes.
Sometimes that can mess with the error bars.
Right. But overall, it's pretty good, right? Most points fall on the line.
Yeah. And the other work that we compared is Kepler 2013. And it's a bigger sample, but it's a sample that is built only on visual methods. So it doesn't have the fitting, and you can see that the fields are a little bit more spread, especially on the lower fields.
Yes, a little more dispersion.
And another thing that is interesting is that they made, depending on the star, they measured the field from H alpha and from H beta separately. So sometimes they have 2 different measurements for the same star, based only on the horizontal displacement of the lines. And there's something interesting that the code that we are using takes into account in a different way, because we can explain how different lines can be affected different, because you can sum a dipole that has, imagine you're seeing the stellar disk, and you can see the pole here and has a very high magnetic field in this region, but the other region has a lower magnetic field. So some lines, you can see the effect of lower fields and others with smaller fields. So it's something that we are already taking into account when you make the model, and not only observing each line.
Yes. So YAWD.
Yes, so we can go to the next figure.
Okay. Very cool. Okay, so we got spectra, we got comparisons, and whoa, there's a wild one. What are we looking at here?
Here, it's just to illustrate is how the behavior of the absorption lines with magnetic field. So in the x-axis, you can see the
wavelength.
Oh, I forgot the wavelength. Yes, that's the word. Thank you. And the y-axis is the magnetic field. You can see there is also in log scale. So you can see that at low magnetic fields, the field is well behaved. We can even approximate with perturbation theory.
Yeah.
But as the field gets higher, especially higher than 20, 30 megagauss, you can get everywhere. You can no longer use perturbation theory.
Right.
You need to consider the other potentials, like it goes like in a square or in the fourth power, and it gets very crazy. We call this spaghetti because it looks like a spaghetti that is going everywhere.
Yes.
So this is good to show that the first thing that is, since we are dealing with low resolution spectra, we want the less noise possible. And usually the redder it gets, the more noise we have because of the instrument we are using. So if we can cut the spectra and throw the rest away, is easier because the rest that we are throwing away is a lot of noise and not actually important data. So we know that until 25 megagauss, 30 megagauss, the field is not gonna get past 7,000 angstroms.
Okay.
So we can cut 7,000 angstroms afterwards.
Bang.
To do not introduce more noise in our measurements.
Correct. I'm with you. Very cool. That's a wild figure. Okay, that's that one illustration, and then here we go with an actual spectra. Okay.
So it's very nice that we are doing this to this big sample that before it was only like 1/4 of the size, but we couldn't do it for everyone. So for every star, because some stars the code didn't converge to an answer, especially because sometimes they can find local minima and it gets trapped into there and cannot find the field that we want. So what we did for these cases where the code was not converging, we looked visually, which was the other method that was already being used.
Right.
So this is an example of the red lines here are the spaghetti lines that we saw before.
Yes.
So we can try and visually match where we see the lines with the magnetic field. So this would be a visual determination of the magnetic field of around 85 megagauss.
Okay.
With this approximate determination in mind, we can then put the code with the magnetic field fixed. So instead of searching for the best magnetic field, it changes only the inclination and the offset and try to make a best fit.
Okay. Okay.
So it helps the code when the code is not converging to the solution.
Right. Gives a little.
And we
nudge.
Also had to do that for fields that are smaller than 1 megagauss, because our code works with the lower limit of 1 megagauss, but some of the stars have slightly lower magnetic fields. And we use, in these cases, we use the visual line inspection.
Yes.
So if you go to the next figure, you're going to see an example of a spectra that has lower magnetic field. Yes, I think it is the next one.
Yeah, this one's about 8 or so, 10 or so. Okay.
No, sorry. The next is actually an example of the magnetic field we determined visually, and then we fixed on the code, and this is what it resulted. So you can see that it's good as a good result. It's not that good. Like if you look at H alpha, you can see that the lines are not very well determined.
Right.
But the magnitude of the magnetic field is well determined, which is the main point here.
Right.
Maybe
Right.
the geometry is not the best one, but the order of magnitude of the field is good.
Cool. Okay. Good. Good.
And in figure 6 is actually what I mentioned before, is the example of magnetic field below 1 megagauss.
There's one. Oh, yeah. Okay.
The bottom is H alpha, and the top is the other lines, H beta, H gamma, etc. If you look specifically in H alpha, is where it's easier to see. So you can see that there is a split in the bottom of the line.
Yep.
H alpha is the bottom.
Bottom one.
Yeah. So you can see that the visually it looks close to 0.8 megagauss. The space between the lines, the separation of the lines. But we cannot make a model because the models are limited to 1 megagauss. So to do not leave without a measurement of the magnetic field, we use the visual inspection.
Okay, got it.
That
was a brain loop on my part.
I think we can go to the next figure, figure 7. I think it's the beginning of our results.
Mass magnetic field. Ooh, there we go. Nice figure. Okay.
Yeah. So this is something I mentioned before, and it's very interesting. It is the fact that you're looking to the whole disk of the star, and the star, we are not expecting it to be uniform, the magnetic field in the whole disk. So the small plot inside, the black one, it shows the intensity of the magnetic field over the stellar disk, and it's with respect to the angle to psi. So how you can interpret this graph better is like the darker it gets, the bigger the region of the stellar surface that has that magnetic field strength. So you can see here that around 30 megagauss, there is very dark, which means a very large region of the star has a magnetic field around 30 megagauss. But you can see a tail here that some regions of the disk has fields as high as 120 megagauss, like 4 times the main stellar disk.
Right.
How can we represent this better? Like if we were doing only visual inspection, we would see, then we have the visual inspection here. The blue lines are the visual inspection, the spaghetti, and you can see that in the visual inspection, it would be a magnetic field around 20 megagauss, 30 megagauss maybe, because it's how we see the splits, especially in H alpha. But you can see that it would result in a different magnetic field for the other lines like H beta and H. We cannot well describe the whole spectra with only one field.
Right.
And and you can see that the red line, which is the model, it's actually doing a pretty good job at with all the lines. And this is possible because it's considering these various strengths. So it's summing a field that is of 30 megagauss, but it's also putting a component that is about 120 megagauss. And with the sum of the whole stellar surface, you have a better description of the observation.
Very cool. Okay, I'm with you. Good.
So nice. A summary of our results basically is most of the fields that we determined are around are smaller than 5 megagauss.
Okay.
Some of it, and maybe because of a bias, because in the spaghetti plot that I showed you, it shows how well behaved the magnetic field is under 20 megagauss and how widely behaved it is over. So it's easier to identify visually. You can better say that this is a magnetic white dwarf when the field is lower, and it gets harder and harder to visually identify when the field gets higher. So that is a bias that we know that is in our sample, but the amount of stars that have lower fields is so high
Yes.
that we believe there is actually a physical behavior behind on top of our bias.
Okay.
Our bias only would not be responsible for such a high detection rate of lower magnetic fields. So we believe that lower magnetic fields are actually more common in nature.
Yes. Yes. Or
So this is what this graph is showing. Is a histogram of the intensity of each magnetic field and the number of stars that has each magnetic field intensity.
Nice. So most of them have 30, 40 megagauss. Okay.
Actually, smaller than that. Most of them has like
it's a log.
3 megagauss.
It's a log. Sorry. Take the
Yes,
log.
it's a
Yeah,
log.
I missed the log here. Very good. Okay. Thank you.
So with that in mind, we can keep going.
Okay. Let's see. Histogram. This is Gaia. Okay.
And one of the most important things that we want to do is not to only know the strength of the magnetic field, but the relation between the magnetic field and the other quantities of the stars, the other characteristics.
Right.
So we want to know if it affects the evolution and stuff like that, and to get relations that can help us maybe determine the origin of this magnetic field. So what we are investigating here is the relation between the mass and the magnetic field, between the temperature and the magnetic field. So the first plot is a histogram of the mass, and you can see in the red line the dA sample from SDSS, and the blue line the magnetic dAs. So you can see that the white dwarfs with hydrogen-dominated atmospheres, everybody, it has a dispersion around 0.6 solar masses, and it's very steep, the dispersion. And while the magnetic ones, if you take out only the magnetic ones, is a broader distribution. And it's the center of the distribution is shifted closer to 0.8 solar masses.
Right.
This is a result that was already established in the literature, that the magnetic ones are usually more massive than the non-magnetic ones.
Okay.
And this only corroborates with this result.
Good. Very nice. Okay.
In the next plot, we can see that through a different light, which is it may be easier to see or not. Like in the first panel, you can see the mass and the magnetic field. So instead of a histogram, you can see the more spread. So it's clear the overdensity around 3 megagauss that I mentioned before. It's basically a line horizontally that is overpopulated. And you can also see that the most magnetic ones are the most massive ones.
Yes, in general, yes.
You can see that in the less massive ones, in high magnetic field, there is a void there. There is no detection in our sample.
Yes.
So this is one of our first results, which is like the higher the mass, the higher we measure the magnetic field intensities.
Very cool.
And in the right plot, you can see the same relation, but studying it with temperature instead of mass. So you can also see the overdensity around 3 megagauss, the horizontal line, but you can see a similar behavior in temperature as in mass, that the cooler the star, the higher the magnetic field intensity. So with these two information in mind, we wanted to investigate crystallization, because crystallization is a quantity that depends on the mass and the temperature, and the higher the mass, the earlier it crystallizes. The lower the temperature, the more crystallized it is. So since we are identifying that the more massive ones have higher magnetic fields and that the cooler ones have more magnetic fields, we're like, maybe we should investigate if it has something to do with crystallization.
Right.
And in the literature, there are already articles that shows, for example, mechanisms that can happen when the core starts to crystallize, and there is it forms a convection layers with a dynamo, similar to the dynamo that happens in Earth. Our core is solid and it's spinning, and it's related to the one of the other quantities that would make us interested is in the rotational period of the magnetic white dwarfs. So we know that this mechanism works for Earth. We have models that suggest that it may happen in white dwarfs as well. So we wanted to investigate that observationally.
Okay, I like that analogy of Earth. That was well done. Very good. Cool. Okay.
So we can go to the next image.
Okay, it's DH.
Okay. I got ahead of myself.
All good.
This section is actually just discussing the temperature of the star. I'm gonna go very quickly through it. Not explaining every plot. It's basically to show, like, we know that the magnetic white dwarfs cool faster when they are hotter and is lower when they are cooler. So the result of this is that we would see an overdensity of cool white dwarfs because they take longer to get even cooler. So we would observe more white dwarfs with 8,000 Kelvin than white dwarfs with 800,000 Kelvin. So
but okay, yes.
That could be an explanation of why we see so many high magnetic fields in cool white dwarfs. And we wanted to prove that that was not the case here. The thing is that we were actually seeing more magnetic fields higher at cooler temperatures. So what we did was the ratio between the whole sample of DAs and the sample of only the magnetic white dwarfs. So when you see the fraction, you see that the fraction is actually increasing. It's not only because there are more white dwarfs at that temperature, it's because the ratio of magnetic white dwarfs is higher.
Yes. Okay. Good.
That whole section is a discussion basically to say that I think we can keep going to more interesting results.
Okay, DH, let's go down to figure 13. How about mass versus effective temperature? Crystallized.
Yes.
Ooh, here's your crystallization curve. Okay, very good.
That's the figure that I wanted to get. This is for me, oh my God, amazing picture, amazing figure. I love this plot.
It's very beautiful.
Because it makes so easier to visualize what we were trying to visualize, and to see it happening was awesome.
Very cool.
Especially because when I first started my master's, I imagined that the crystallization would not be a big impact, because the main hypothesis when I started my PhD were the debate was being between the fossil fields and the binary evolution. And I imagined that we didn't have back then, when I started my master's, that many crystallized stars detected. So I imagine that's not going to be a big effect. But then by the end of the work, we were like, oh, that's interesting. So this plot shows the temperature in the x-axis. You see that it's inverted, as all the other plots in temperature, and astronomers love to do that. And in the y-axis is the mass. So here, as the star evolves, the white dwarf evolves, it cools. So the star is traveling from left to right.
Yes.
And the black line is the beginning of crystallization. We have models of how stars evolve, and we can model based on the mass of the star, because the pressure is going to change inside, and the temperature. When the core of the star will begin to crystallize.
Yes.
So this is the black line. They are from evolutionary models. You can see that the black line is not continuous. It's like it has some zigzags.
It's got some zigzags right here.
Yeah, that's not a physical effect. It's only the difference between different models. Because the models, usually they're like only between a specific range of temperature. So I had to some different models. So this line is a composition of different models to make the whole line. So the difference between one model and the other, you can see that the
It
zigzag
sometimes
line.
gets jumps, but if I smooth it out over my head, you know, it's a
Yeah.
you can smooth that.
That's something interesting to keep in mind is move it out.
Yeah.
So the color of the dots, the gray dots are the white dwarfs with fields below 10 megagauss. So as I said, most of the stars have fields below 10 megagauss.
Okay.
And we are not considering that strong fields in this context.
Yes.
Like 10 megagauss is a very high field if you compare to for example, the magnetic field of the sun, which is the order of Gauss and not megagauss.
Yes.
But in this context, 10 megagauss is going to be considered a low magnetic field.
Yes.
The blue dots are the magnetic field a little bit higher until 100 megagauss.
Okay.
The intermediate magnetic fields, and the red ones are above 100 megagauss. So what we are considering the high magnetic fields. So the interesting thing here is the gray dots, they are more evenly distributed.
Right.
And the blue dots, you can see they are tending more towards lower temperature and higher masses, but is still very well distributed.
Yeah.
But when you go to the very high magnetic fields, the red dots, they are almost all of them over the crystallization line.
Right. Right.
Some dots, there may be some uncertainties on the measurement of the mass and the temperature. So we cannot, especially this dot that is close to your pointer, we cannot, the red dot close to your pointer, we cannot say that, yes, that has not started crystallization yet. You cannot affirm.
Right.
But if you look closely, there are two red dots that are shaped as stars.
Right here and right here.
These two stars are very special because they are the highest magnetic field that we have measured, like 700, 800 megagauss.
Wow.
And it's very interesting that one of them is over the crystallization line and the other is not.
Correct.
So one of the hypotheses that we have for this is that they have different origins of the magnetic field.
Okay.
We imagine that this one that is not over the crystallization line may be coming, for example, from a merger product. Awesome. So in the future, a possibility is to investigate closely specific this star to see if it has any other characteristic that would indicate that it comes from a merger.
Right.
Because we know that mergers could generate very high magnetic field intensities.
Mm-hmm.
So there are exceptions. We don't expect every star of every magnetic field to come through the same origin.
Channel, right.
Like the same channel, yeah. Nature has different ways to make things, and we have to deal with that. But what we want here is just a general behavior. So what we believe is happening here as a general behavior is that the higher intensity magnetic fields are, if not being generated, at least being intensified by the dynamo in the crystallization process.
Yes. Very cool.
You can see that the lower magnetic fields stars, they don't need a crystallization core to have these magnetic fields. It can have a different origin. It can be a fossil field. It can be from mergers. But the point is the very high magnetic fields appear to be boosted by the crystallization.
Right. Right. This is an awesome plot. Very nice. Very nice.
I'm very happy about it.
Yeah, that's a very, very cool plot. Okay. Awesome.
That's the main point of this article. After this, we discuss some specific cases. So if you go to the next plot,
Spectra.
This is a very interesting star. All these 5 spectra are from the same star. And if you look closely in each alpha, you can see that the blue spectra, the middle one, it has 3 components. That you can see very clearly the 3 components. But if you look in the green line or the red line, you're going to see that the 3 components are not so clear.
Yeah. Why
And
is
if you
that?
go to the H beta, you can also see that one of the components of the H beta, it's appearing and disappearing. What we think is happening here?
Yes. What's
We
the
think it's because the star is spinning. If
okay?
you look at the observation date, they are all from the same year,
Yeah.
not from the same month, but closely the interval of observation is less than 1 month.
Yes. Okay.
So what we
Wow.
think it may be happening here is that since there is a dipole and it's inclining in one direction and the
Oh,
star may be spinning, when
yeah.
you are looking
Sure.
straight through the dipole, you see a distribution of magnetic field. When the star spins and you're no longer looking straight at the pole, you'll see another distribution of magnetic field over the stellar surface.
Changing look white dwarf. How about that?
So
Uh,
that's very interesting, and that's something that we are investigating further. Actually, this is
yeah,
a
I was going to
part
say
of
because
our future work.
yeah, at the right cadence, then you should be able to draw out the rotation period.
Yes.
Right. Exactly. Good. Wild.
So yeah, that's a very interesting thing that it's ongoing, a work ongoing.
We'll come to that.
And if you continue, there is another example. There is a very interesting star.
Okay.
Yes. This plot shows the comparison between using a centered dipole and an off-center inclined dipole.
Okay.
So previously in the literature that has been other measurements that were of center dipole. And here is an example. If you see the dotted line, not dotted, it's
dashed.
Yes, the dashed line. If you see the dashed line is an example of a center dipole. If you see the full line is an offset and inclined dipole. And you see that the offset inclined dipole does a much better job describing the observations. So both of them has the same magnetic field intensity. One is the difference between them is only the off-center of the dipole and the inclination. So one thing to keep in mind as you compare data between the literature is that, because like sometimes you can have the magnitude of the magnetic field correct, but the model, it may not be so good because of the inclination and the offset. And sometimes you may change the magnetic field intensity trying to mimic the behavior of the observation, but it's not gonna get that if you do not add an offset.
Yeah, you won't get very far with that. It's physically a different.
And the next plot is similar to that. Is from an example from the literature. Is a star that has been studied in another article. In the other article, it says that they could not find a model that represents the depth of the line well. And this is an example of how you could pretty well represent. There is only one of the components of the H beta that is not very well described.
Right. Easier.
But generally it works.
Yeah, globally, a few little misses here and there, but generally pretty good. Very nice.
Cool. This star in specific is treated in the literature as having, the other article says that it may have helium in the atmosphere, because when there is helium in the atmosphere, the pressure changes in the atmosphere and the depth of the line that you observe can change. So he justifies the depth of the lines with the presence of helium in the atmosphere. But one of the things that is different from the fit that the other article presents and our fit is the temperature of the star. The temperature that they determined is a little bit different than the temperature that we determined. So there's also something that, as I mentioned in the beginning of our talk, determine the depth of the line. So that's another thing that can affect the depth of the line, but not the other of the magnetic field, the order of the magnetic field that they determined is similar to ours.
Okay. Okay.
Even like the other physics involved may be different, but the magnetic field is the same.
Okay. Very nice.
So that's basically it.
Very cool. Very, very nice article. Larissa, I want to thank you so much for walking us through this very awesome APJ article. Thank you.
It was a pleasure.
And you touched on it a couple times as we walked through, so I'll push on it a little bit. So where do you think we go with this over, let's say, the next 2 to 5 years? Is there more observations being taking place? Can we do DBVs? So can we do helium-dominated atmospheres? Is there stuff to do on the theoretical models, both of the white dwarf itself and on YAWD on Hatton? So just sort of where do we go over the next steps, or one's PhD thesis? I don't know which, but just sort of, where do we go over the next couple of years on this topic?
So the first important thing to say here, and I'm sorry I didn't mention it before, is that white dwarfs with hydrogen-dominated atmosphere is like 80% of white dwarfs.
Yes.
So that's why we chose to start with them, like, because they are simpler. Obviously, like, it's easier to make a model of a hydrogen than a helium, for example.
Fair enough.
But they are 80% of the stars, so most of the stars are gonna be in this class.
Okay.
But yeah, it's possible to make this study for white dwarfs with helium-dominated atmospheres. Actually, there is a work that has been done after I published this article that's published the models with helium-dominated atmospheres and study some specific stars. That's a very interesting point going forward, but it's not gonna increase that much the whole sample,
the total,
because
only 20
is a smaller to begin with, because there are fewer stars with helium-dominated atmospheres.
Okay.
Another interesting thing is that we have always space to improve in model-wise. Like, these models are only from 8,000 Kelvin higher, so the stars with lower temperature, it could be better modeled. But that has been also this other work from Hardy, Francis Hardy, his name. His PhD was doing these models with temperatures from like 6,000 Kelvin and above, so it makes bigger. The results were published also after I finished this, and mainly the results are that it doesn't change the intensity of the magnetic field, as I mentioned. Like, it may be a model that represents better the observation, like it can reproduce the shallow features, but the intensity of the magnetic field is not going to change.
Right.
It's the same.
Okay.
So another thing that we assumed in our model was log G equal to 8, which is good for DAs in general, but it's not good for the magnetic ones because they are a little bit more massive.
Okay. Okay. Yes. No,
but
shrunk.
In this work that Hardy did, he also made the log G variable, and he also found that the intensity of the magnetic field is not going to change. The best you can do is going to be fitting better the depth of the line. So overall, I don't think it's very interesting to go in making the models a lot better, because what we have now is already good enough. Someone already did a little bit more depth in that. So I think we can use what we have now. The best way to go, I think, is to get a larger sample. So to keep an eye on other surveys with spectra, with resolution good enough to observe this. And I think another thing that is gonna come more in the future is the relation between the rotational period and the magnetic field, because for the crystallization dynamo to happen, that's something that is important. And there are still few stars that have the rotational period and the magnetic field studied. So that's a sample that I think is gonna get larger. I have already seen, I think, 1 or 2 articles after I published mine going in this direction. So I also have an article there is ongoing. I'm writing it right now with data from SOAR. So I got spectra from some of these stars, and we are actually taking data from TESS, with Transiting Exoplanets Sky Survey, and taking the photometry to find variation in the light curve to try to determine the rotational periods of the stars. But since the TESS camera has such a big field of view, and the white dwarfs are so faint, we cannot guarantee that the signal we are measuring are actually coming from the white dwarf. So it's always good to have data from Earth. That's why I chose SOAR, for example. So we can make observation and confirm the rotational period. And on top of that, we can make spectroscopy, time-resolved spectroscopy, as the plot I showed you, like to see the lines varying as the star is rotating. And I think that's a very interesting way to go from here.
Cool. Very cool. Well, I really look forward to seeing this topic evolve over the next couple of years, and especially your next article. So very cool. Very nice. And that will do. Larissa, thank you so much once again for walking us through your very lovely article.
Thank you.
And that will do, everyone. I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.